Hello, my name is Dr. Margherita Malanchini, and today I will be presenting on genetic approaches to investigating the contribution of non-cognitive skills to academic achievement or development. So we know that several factors contribute to individual differences in academic achievement, and these include home, school, and neighborhood environment, perinatal and growth factors, motivations, cognitive ability. And we also know that one source of variation in academic achievement is genetics. However, it is often assumed that genetic factors would contribute to academic achievement through cognitive ability, and so that academic achievement is partly heritable because cognitive skills are heritable. However, converging evidence applying different methodologies, including twin studies and more recently DNA-based methods, points to the heritability of academic achievement beyond cognitive skills, which itself points to the contribution of other so-called non-cognitive traits to variation in achievement and to its heritability. And twin studies have provided the evidence that non-cognitive characteristics such as self-regulation, personality, attitudes, and motivations, for example, all account for genetic variance in academic achievement beyond cognitive ability. Twin studies have helped with establishing that genetic variation in non-cognitive skills is in part shared with the genetic variation in academic achievement, and importantly, that these shared genetic factors are not simply accounted for by general cognitive ability. And this is really a fundamental first step in the quest to uncover the molecular basis of educationally relevant non-cognitive skills. But until recently, a number of challenges prevented research into the molecular genetic basis of non-cognitive skills. And some of the core challenges are the heterogeneity in the association between these non-cognitive measures and education, poor test-retest reliability often observed for these non-cognitive measures, the lower heritability of non-cognitive measures, and most prominently, the fact that these measures are not often included in large genetically informative cohorts. However, one way of overcoming these challenges starts with the definition of non-cognitive skills themselves. So if we are willing to embrace a popular definition of non-cognitive skills, which comes from the field of economics, as all contributions to educational attainment that are not cognitive skills, then we can find a way around the many challenges previously described. And in fact, we can leverage information from well-powered existing genome-wide association studies. So genome-wide association studies are concerned with discovering how genetic variation across many, often hundreds of thousands of loci in the DNA, which are called single nucleotide polymorphisms or SNPs, relate to individual differences in observed traits from height to schizophrenia to personality. And one of the largest and most successful GWAS studies in the behavioral sciences looked at educational attainment and uncovered over 1,200 loci in the DNA that are significantly associated with how far people go in education. And now we can leverage information from well-powered existing genome-wide association studies, and particularly those of educational attainment and cognitive performance, to create an in silico GWAS of non-cognitive skills. And this is what we did in this very recent study. So we leveraged well-powered GWASs of cognitive performance and educational attainment to obtain a GWAS of non-cognitive skills. And this was possible thanks to a recently developed genomic method called genomic SEM that allows to apply structural equation modeling to genomic data. With genomic SEM, we can use these GWASs to separate the variance in educational attainment into a cognitive and a non-cognitive component, or a residual. We want the non-cognitive component to be the variance left after subtracting cognitive performance from educational attainment. And so we called this a GWAS by subtraction. And in this GWAS by subtraction, we are defining two latent unmeasured factors. One latent variable that we called COG, which reflects the effects shared between educational attainment and cognitive performance, which is indicated by the blue circle here, and the second latent variable, which corresponds to the effects on educational attainment that are independent of cognitive performance. And we called this variable non-cog for non-cognitive skills, and this is indicated by the orange circle in the slide. And we examined the association between the genetics of non-cognitive skills and differences between people in important life outcomes, applying two methods, genetic correlations and polygenic scoring. So the GWAS by subtraction allowed us to decompose the SNPs associated with educational attainment into cognitive and non-cognitive genetic variants. And non-cog genetics were found to be related to genetics of several favorable life outcomes, from educational attainment to socioeconomic status and self-regulation and adult health behaviors and personality, for example. These in-depth phenotypic annotations have provided us with the earliest insights into the molecular underpinnings of educationally relevant non-cognitive skills. However, it remains unclear to what extent the non-cog genetics relate to education-related non-cognitive skills and to academic achievement over development. And this is what we are currently working on with Andrea Allegrini at UCL and several other collaborators. We are bringing the GWAS by subtraction into a developmental educational context. And we are examining how the genetics of cognitive and non-cognitive skills contribute to academic performance from age 7 to 16. And we are triangulating findings across multiple genetic methods, looking at evidence using both DNA-based and family-based approaches. And why triangulation? So since different genetically informative methods are subject to different and unrelated assumptions and limitations, triangulating findings across multiple methods provides a powerful tool to increase the reliability of results and consequently push forward scientific knowledge. We applied the twin method, which very briefly allows to estimate the genetic and environmental contribution to a trait by comparing monozygotic twins who share 100% of their genetic makeup and dizygotic twins who share on average 50% of the segregating genes. And so we used both the twin method and these newly available DNA-based methods, starting from the GWAS by subtraction that I previously described. And we conducted our investigation in the longitudinal twins early development study. So different measures of non-cognitive skills were available at different developmental stages, and these were provided by multiple raters, including parents, indexed by the P in the slide, teachers in green in the slide, and also self-rated by the twins shown in blue on the slide. And in order to provide a holistic view of the association between non-cognitive characteristics and academic achievement, we proceeded through different levels of analysis. So first, we considered individual non-cognitive measures. And second, we adopted a global level of analysis by creating latent constructs, which represented individual differences in broader educationally relevant non-cognitive skills, such as academic motivations, attitudes, and socio-emotional competencies. And so here are the educationally relevant measures of non-cognitive skills that were available at different ages across different raters. At age 9, data on non-cognitive skills were available from parents, teachers, and self-rated by the twins. And at age 12 and 16, they were only available through self-reports. Different educationally relevant non-cognitive measures were available at different ages, and these were differentially associated with academic achievement at the same age, as it's represented by the length of each of these bars. For example, stronger correlations were observed for self-efficacy and self-perceived ability and achievement over development, while the smaller associations were observed, for example, for measures such as classroom satisfaction or school enjoyment. And we created latent factors of educationally relevant non-cognitive skills separately for ages and raters, including the measures available at each age for each rater. And these latent factors provide an index of variation across a broad spectrum of educationally relevant non-cognitive skills that capitalizes on the covariance between non-cognitive skills measured at each developmental stage. The results I will discuss from now on are obtained using these broader latent dimensions in the interest of time. So this plot shows the association between the latent non-cognitive measures at ages 9, as rated by the parents in red, the teachers in green, and self-rated by the twins in blue, at ages 12 and 16. So the association between these latent non-cognitive measures and academic achievement at the same age. And the blue dots show the effect size of the association between these non-cognitive measures and academic achievement. And although the strength of these associations varied, we can see that non-cognitive skills are positively associated with academic achievement at every stage during compulsory education. And if we look at the gray dots and gray line, we see that non-cognitive skills remain positively and significantly associated with achievement even after accounting for general cognitive ability when using a multiple regression framework over development as well. And we can really ask the same question. So to what extent non-cognitive factors are associated with variation in academic achievement beyond cognitive ability using a genetically informative framework? And this can be achieved applying a Koleski decomposition to twin data, which is a multivariate twin method that works similarly to a hierarchical regression. So the full length of the bar here represents the total variation in academic achievement. The red portion of the bar indicates the proportion of the total variance in achievement that is accounted for by genetic factors. As you can see, the red bar includes different shadings. The lighter shade of red indicates the proportion of the genetic variance in academic achievement that is accounted for by the genetics of cognitive ability. The slightly darker shade of red, and this is what we really are interested in, shows the extent to which the genetics of non-cognitive skills contribute to variation in achievement above and beyond the genetics of cognitive ability. And we can see that there are significant genetic associations between non-cognitive skills and academic achievement at every stage during compulsory education after accounting for the genetics of cognitive ability. And now, thanks to the GWAS by subtraction, we can ask the same question using DNA-based methods. We calculated cognitive and non-cognitive polygenic scores in our independent sample of over 10,000 twins from the Twins Early Development Study who had DNA data available. And polygenic scores provide an index of an individual's genetic propensity for a given trait that is constructed by adding up the genetic variance in the DNA weighted by the effect size of the contribution to the trait, which are obtained from genome-wide association studies, summary statistics. So we obtained these from the GWAS of cognitive and non-cognitive skills, and so we calculated polygenic scores for cognitive and non-cognitive skills. And so going back to the question, so to what extent the genetics of non-cognitive skills contribute to academic achievement beyond the genetics of cognitive skills at every stage in development? Here we can see the extent of their contribution, which is indicated by the orange dots, and the contribution of cognitive genetics indicated by the blue dots. When we included both polygenic scores and all the relevant control variables in a multiple regression. As you can see, non-cognitive genetics contribute substantially to variation in achievement at all developmental stages, but not only that. While the role of cognitive genetics remains relatively stable over development, the role of non-cognitive genetics increases over development, and we will go back to this point in this presentation. So as part of this project, we have also worked at extending the GWAS by subtraction model. And this was done for two key reasons. First, we wanted to increase the power of the cognitive genetic factor in order to obtain a more precise and targeted estimate of cognitive skills. And this is why we included summary statistics from several other GWAS of cognitive traits, from processing speed to executive function. So in addition to the cognitive performance GWAS. And second, we worked at creating a more powerful non-cognitive factor by including GWASs of other traits known to be associated with academic achievement beyond cognitive ability, such as, for example, socioeconomic traits. And this could result in a more efficient separation of the genetics of cognitive and non-cognitive skills, and consequently a more refined cognitive polygenic score and a potentially more powerful non-cognitive polygenic score. And the new polygenic scores correlated at 0.8 with the original polygenic scores obtained with the GWAS by subtraction. So one of our burning questions was related to educationally relevant non-cognitive skills. So do non-cog genetics actually reflect genetic variation implicated in educationally relevant non-cognitive processes? And we found that yes, they do. And this is shown by the orange dots in the plot. Really, we showed that the genetics of non-cognitive skills was significantly and positively associated with education-related latent measures of non-cognitive skills over development. And the only exception was self-rated non-cognitive skills at age 9. And this is also consistent with what we found from twin studies. And this could potentially reflect the difficulties that young children may have in reflecting upon themselves and their thoughts, feelings, and behavior, and therefore the struggle that they might have in providing an accurate account of how motivated, interested, or confident they are in learning. And however, the new non-cog polygenic score performed only marginally better, but overall similarly to the original score, as it's indicated by the red dots in the plot. The new cognitive polygenic score, which is represented by the dark blue dots, was overall less associated with non-cognitive skills than the original cognitive polygenic score, which potentially indicates that it was more reflective of the fluid, not learned aspect of cognitive ability. And this is also evident in the association between the new cognitive polygenic score and academic achievement. This overall seems to indicate that the new extension of the model provided a more refined estimate of non-education or culture-dependent cognitive skills. On the other hand, the new non-cognitive polygenic score did not result in a substantial increase in prediction, as it's indicated by the similarity between the red and the orange dots. But overall, the previously presented pattern of increasing the contribution of non-cognitive genetics to variation in achievement over development still remains. And this is important because several studies have found that the polygenic prediction of academic achievement increases over development. And here we provide preliminary evidence to what seems to be driving this increase. It doesn't seem to be cognitive ability, but it seems to be more non-cognitive skills. And we might wish to take this even a step further. So evidence of increased heritability and genetic prediction over development are consistent with the existence of gene-environment correlation processes, which is that the exposure to the environment does not happen at random, but is in part correlated with genetic disposition. So as children grow up, they are more and more able and inclined to shape their environment and their experiences based on their genetic propensity. And this is likely to result in these increased heritability estimates and polygenic prediction over development. And here we provide a first glimpse into a potential explanation of how this might happen. So this seems to be happening through non-cognitive processes such as motivation and affective processes rather than through cognitive skills. So, but why studying the genetics of non-cognitive skills and why try to increase predictive power? So among the many reasons why I think this is important, I thought to flag a few. So I think it's important to consider all the factors that contribute to academic achievement over development. And parsing the contribution of cog and non-cog genetics to academic achievement might offer important and portable tools to uncover mechanisms. And increasing and refining prediction are the first steps to explore these potential environmental and biological mechanisms. So to wrap up, here we provide a first glimpse into the genetic basis of non-cognitive skills and their association with educationally relevant developmental outcomes. We found that non-cognitive genetics predicted educationally relevant non-cognitive skills at all stages during compulsory education, and that non-cognitive genetics predicted achievement at every stage over development, and that their predictive power increased over development, potentially indexing these mechanisms through which gene-environment correlation is manifested in the higher heritability and polygenic prediction of academic achievement. So these results, we found that our results were consistent across multiple methods. And really, we think that these genetic discoveries might provide a good framework for the investigation of biological and environmental pathways. And with this, I'd like to thank all my co-authors, particularly the wonderful Andrea Allegrini and the Twin Cell Development Study Sample, and you for your attention.